they were back at the whole thing with the codebook. It's it's a messy month, so it's gonna be a messy stream, and yeah, I don't know. We'll see. I can't really promise I do now regular streams for the next days. It's complicated. So, but never give up. Anyway, I keep I think I keep obsessing about this stuff here. I just because it just makes in a weird way no sense because I'm like, okay, now I realized I'm stupid because here is like literally I was like complaining in the last video that okay, we're not told how you specify the black box, but you're literally told. You're like, we will assume that black boxes can be described by conditional probabilities. So if that's how you describe it, then it makes sense that you do this at the state level, right? So probability of absorbing y given given x, right, as an input. And so that makes the first part completely easy to derive because then you're like, okay, so I have um, 2 to the power of n possible input states, and for each 2 to the power of n, if I just go brute force and I assume everything's independent, I have to specify I need 2 to the power another 2 to the power of n probabilities because of, to kind of specify the transitions between these. And so that 2 to the power of n times 2 to the power of n is 2 to the power of 2n. Um, and I get from the solution, right? Like, okay, I get that, sure, the things must add up to 1, right? Of course, you can just use the probabilities to define that. This is just an additional constraint on what are the things that you can do, right? Now, how that this translates into having less, um, this is what I don't. I think I'm just gonna skip this for now, and I'll keep obsessing about this offline on Twitter because it says the probability. So yeah, so the probability of given an x, the probability distribution, like this is definitely not just like a, you know, a a uniform distribution, right? Or even like whatever we know that this has this constraint that the probability of all the y's you can observe given a specific x must add up to hmm, wait a second. Am I just saying bullshit? Yeah, okay, the probability must add up to 1. No, yeah, that's correct, must add up to 1, right? Because you cannot have like 200%, right? um but how does this map to like a reduction on the variable on the variables that are needed to specify the black box, right? You know what I mean? Like all the ways that I can logically think about this, like, okay, so I have to add a constraint, so I have to add variables to the whole thing, right? I have to add um maybe I'm just too much, I'm being driven too much by how the solution is written. And maybe I should just kind of try to think about these without reading, it's going to be hard to unread, of course, now, but without actually having that in mind. And say, look, I have now all these. Like, is there a way that I can reduce these? So I have all the different probabilities. And for a given x, I have like 2 to the power of n, right? Um, of course, that's a probability distribution. So some of these probabilities will be zero or just not be there. Hmm. So 2 to the power of n constraints, one for each configuration x. But how is that constraint then represented, right? Because here we're saying how many variables I need to describe. Show that independent that these number is the independent probabilities that are required to specify a black box, right? I don't know how to find, because for each set for each given x I have a probability distribution, but how is that probability distribution just encoded into one probability that I need to subtract from the amount of different probabilities, right? You know what I mean? If anything, it just feels like you should be adding things to add the constraints. But I might just be wrong. I don't even know how could I Google that. Actually, let me just go into incognito mode. I'm going to incognito mode. Just have also a cleaner search and stuff, right? Because I don't even know, I wouldn't even know how to search for these. I don't know, my common sense, it's probably stupid, but my common sense says you should be adding that because it's constraints. So you're adding information to constrain. You're not removing information. You know what I mean? One for each configuration X. Probability constraints. Maybe we should start here. You know, that's a good exercise, actually. Just how to factor out even find these things, like chance constraints. Probability constraint. No. I don't even know. That's definitely nothing to do with these. I'm determined to find this out. This is going to be probably the most boring stream ever. But that's probably going to kill me. I should just really go on. Um, I can visualize that, right? I have a map of all the possible input states, all the possible output states. For each input state, there's like 2 to the power of n different probabilities that specify kind of uh, the probabilities of observing a given y, right? We have a constraint over each of these probabilities, though, which is that over each of these probability distributions, right? Give me a second, someone call. I'll take it later. We have a constraint over, we can call these, let's focus on one, it makes sense, right? So let's focus on one specific part of map, which is we pick an x, and then there are to the power of n different arrows, right, or probabilities that go to the possible outputs, and they all have numbers, right? Mm, but then there's some sort of constraint there. This means that these numbers must be adding up to one. How does this translate to kind of one parameter, right? And even if that would translate to one parameter, then you would actually be adding these and not minusing them, right? Yeah, maybe, I don't know. Like, I don't know. I don't know. I guess I'll have to ask someone that's done that before. But I mean, how could I? So, uh, so probability distribution at some constraints, something like this. Uh, maybe that will help generate a list of random numbers of a random variable under given constraints. Second attempt. So whose sum is m? Yeah, okay, but that's just like I'm more like looking for the specification of these, right? Because maybe there's a way to specify such such probability distribution that does indeed require, yeah, I don't know. To me, it seems like it should be a plus. I think I'll just assume it should be a plus. Because you need a constraint. Mm. So it's one. Ah, no, I get it. I get it. You minus one because, ah, that's so stupid. Of course, you minus one because you're minusing one probability because it's going to always be defined by uh, the the fact that it's going to add up to one, right? So you have yeah, so you have 2 to the power of n different probabilities that specify the transitions, but then you don't really need them. The one way to specify the constraint is just kind of take minus one, right? And so you specify 2 to the power of n minus one because the other one is implicit because you just got to take one minus the sum of all the other ones, and and that's the value. If it might be zero or whatever, right? I get it now. Oh God. Okay. Um. Yeah. 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 That's it. That's of course, and it's quite obvious, right? It's actually God, feels good though. Um. Cool. So let's move on to the quantum stuff. The class of quantum systems is of most interest to us, like random classical systems in the quantum system. Oh God, wait a second. That feels good. That's so stupid. It's so stupid. Oh, so what do we have now? Let's pour some more coffee. To be honest, I have as much time as until the baby wakes up. So that's the boss. He's the boss now. The class of quantum systems is of most interest to us. Observations, these outcomes have some curious features that cannot be explained by classical randomness. Let's imagine that our set of n coins are now quantum. So we have n qubits described by a state. There's an important difference in simulating this state of a classical and quantum system. Yeah. So the exercise. No, 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 no. I thought that was the solution. Okay. So there are two exercises. So exercise. How many classical deterministic variables are needed to describe the state of a system? Explain from the perspective why a quantum computer might be useful. Okay, so how many classical deterministic variables are needed to describe the state of a system? So we have n qubits, right? And so here really we just have to describe that, like, the state itself needs 2 to the power of n variables in comparison to, up until now, because any possible linear combination of these values uh, is also a valid state, right? So we have n qubits described by a state. Each coin is a state is a qubit. So here, yeah, so here the linear combinations count as states as well. Is that correct? I think so, right? There's an important difference in whether you state that. So from that perspective, why a quantum computer might be useful? Well, it might be useful because if we are able to have something physical that encodes these n qubits, and we have n things which potentially encode 2 to the power of n other things, right? Yeah, I know that's doesn't mean you have access to this information and whatnot, but you can manipulate it. But I think that's probably where the exercise goes. So the status is described as so it has 2 to the power of n complex amplitudes. In a classical computer, we need a list of all 2 to the power of n components. And in the quantum computer, we only need n qubits to store them. Yeah, exactly. So that seems exponentially better. Yeah. We will imagine we have the ability to prepare the system in some specific configuration X and observe in the computational basis after applying the black box with probability of observing Y given input X. So you have a state X, right? It can be a linear combination of things. So you have specific configuration X. Okay. This looks very similar to the classical random case, and it's tempting to conclude that we could just simulate the n-qubit system using n random beads. In the next exercise, you'll see why this doesn't work. Consider a single qubit quantum circuit consisting of a single Hadamard gate. Again, remember, I mean, that's not the beginning of the codebook, so you should have done all the other, qubit basics and quantum basics before. But I hope that I'll be able to do that, go without that. Consider a single qubit quantum circuit consisting of a single Hadamard gate H. Write down the conditional probabilities for measurement outcome Y after applying this black box to input state X, where X and Y belong to, so there's zeros and ones binary. Give me a second. So the black box is the circuit, right? Let me make sure I read this well. It's I want to make sure I'm reading this well because it's early in the morning. Consider, and the coffee hasn't kicked in yet. Consider, what's more, this is even decaf because my coffee machine broke and I'm waiting for a replacement today. And that's the only thing that I had around. At least I get the flavor. Consider a single qubit quantum circuit consisting of a single Hadamard gate, conditional probabilities of something Y, given X for measurement outcome Y after applying this black box to input X. Okay, that's not that easy. Give me a second. So you have well, but it's a single Hadamard gate. Or is it that it's a, you have a single qubit. Okay, sorry, you have a single qubit. You see, I'm saying, reading well, because I'm like going already here, like, okay, so we have n coins, it's a single qubit, which is in the state like alpha 0, beta 1, right? And you apply a Hadamard gate, and so the probability of measuring the different combinations, so of measuring 0 or measuring 1, right, is basically kind of this alpha times, or this alpha divided by square root of 2 and the beta, like, because the Hadamard, so what the Hadamard does to the zeros, it turns it into the, maybe I should write it down because that's, should I open pen? I'm not prepared for this. So the way that I think about these is that we know that for the state 0, the Hadamard gate turns it into 0 plus, right? So it turns it into these, and for the state 1, then it's the same, but this is minus, right? So if we now have a generic state that is basically alpha 0 plus beta 1, remember this beta can be minus whatever, right? But then we apply, we apply these rules, right? So you basically get like, alpha divided by square root of 2, 0 plus beta divided by square root of 2 of 1 plus beta square root of 2. What? No. What? Not beta. Yeah, beta, of course. Yeah. 0 plus minus. Yeah, wait, that's alpha actually. God. That is alpha, of course. That is alpha plus minus beta, right? So this means the probability, right? So for the 0 will be basically, alpha plus beta divided by square root of 2. And then the probability so this will be for the 0, and for the 1 would be alpha minus beta square root of 2, right? Because you basically, and squared, right? You got to square these things. because these are just the coefficients, right? Which here is kind of what makes you know, like this kind of makes sense if you plug in, like, say, the same value for alpha and beta, then you get that zero because it means you were in an equal superposition. And so the Hadamard is going to take you back to zero, right? I think so. I think so. Oh, come on. Wait, what? That's weird, right? Because you're not telling me. I think I'm not wrong, but I mean, like, it's a single cubic. This qubit is in the state X. If I apply the Hadamard to the state, yeah, but you're missing alphas and betas and whatnot here, right? So it depends what X is. Or is it that they're assuming that X is either 0 or 1? Because that seems to me it's the general version of, like, well, if X is 0, then this exponent is 0, and so you get the 0 plus 1. If this is 1, then this exponent is 1, so this is minus 1. So uh, yeah. Okay, but you get what I did, right? So I think that makes total. That's just like I assumed X could just be any state, right? While they assume X. Yeah, well, okay. Fuck it. They assume it's there. It's right there. I'm just stupid for not reading the. I'm just stupid for not reading the actual text. You see? Yeah, yeah, yeah. But okay, kind of makes sense. Yeah. If that's the case, yeah, that's all. Of course, if it's 0 or 1, the probability is always going to be half, right? If the black box was classically random, call it H, what would be the result of applying it twice? What is the probability distribution after applying two Hadamard gates? So without looking at this picture, I don't know if that tells anything, right, about this exercise, but I'd say, well, if it's classically random, right, you don't get a superposition. Like, you can't get superposition. So this means you apply the Hadamard gate, you apply this H hat or H whatever the first time, you get 50-50 chances of one answer or the other. Then you apply this again, you also get 50-50 chances of one answer or the other, and blah blah blah. You keep getting these, while in the quantum case, once you've applied the Hadamard gate, you stay in a state that it's in superposition. And so if you apply the same gate again, then you go back to the original state because it's a reversible gate, just because it applies linearly to the different components, and then things cancel out because of the interference, which I'm assuming it's all explained in the previous modules here, but I think that is definitely the solution, right? So if your black box is the classic, then the result of applying it twice gives the same thing back. Yeah. So if P1 denotes the result of applying gate P2, then conditioning on the so oh wait, you're actually supposed to specify something. Okay. If P1 denotes the result of applying one classical Hadamard gate, and P2 then P2 then conditioning on the intermediate value y prime, gives a probability distribution. So observing y given x, right? Okay, so they what do they do here? So they do, it's P1 observing y prime over x, right? So the probability of observing, and then it's a sum over the possible values. The probability of observing 0 given 1. Yeah, exactly. Okay. So the probability of observing, for example, 0 given x is 50% times the probability of observing y given the 0 is also 1.5. So this is this, and then yeah, okay. Okay, so generically they specify that probability distribution as a conditioning. So you have the probability of observing something given something, this we know, and then they just add this intermediate value here. Should have done this. Um, yeah, exactly. Exactly. So the harmonic is a different result represented around just okay. Cool. Okay, so we have done the first, we've completed the first point. We've completed the first point. Yeah, okay, so it's always the probability. So this is like, yeah, I'm just always trying to understand how they even frame that as like P2, so the probability of observing Y given X, right? And so they do this with the intermediate value, it's always 1/2. Yeah, okay, cool. Because we know the probability of observing 0 and observing 1, and we know that's all the values that there are. Cool, let's go to the second part. And there's a challenge, so we'll probably go through the challenge first, and then go through the textbook. What do we have here? So in the last code challenge, you will have noticed that the quantum black box could be described by a Hadamard gate. What? Really? This has a peculiar behavior that applying it twice leads to the trivial box. I think the previous code challenge was just like shifting things, right? Oh, they probably mean exercise, kind of. This is in sharp contrast to the random classical black box, which applied twice gives the same random outcome, since it simply flips a fair coin and tells you the result. Clearly, more is possible in quantum mechanics. The more general quantum block is a unitary operator, U, defined by the property that applying U and then adjoin U does nothing. The adjoin is shorthand for yeah, okay. Coder size, write a function which checks if an array of complex numbers is unitary. What? Oh, so I need to actually, okay, so I need to actually just do that probably. Check that the transpose, so so check that the operator times its transpose is equal to the identity, right? Okay. But it's complex numbers. I know there's a trick here. What is all close? Let's check these functions. The adjoint equal with the tolerance. Yeah, okay. So this is to compare the equal. The conjugate, return the complex conjugate element-wise. The transpose and the identity. This the adjoint is a shorthand for the complex conjugate of each matrix followed by the transpose. So I guess you just need to do kind of return NP. So first we do the conjugate, right? Conjugate operator. NP transpose. No. So the transpose of the conjugate. Why is this going on? What is going on here? I have I have too much zoomed in, I think. There you go. The conjugate of the no, the transpose of the conjugate must be equal. So I just have to say NP. Is it all close like A and B? So basically all close these, and then oh, of course. Well, I have to do the operator times these, right? I guess it's a normal product. Yeah, yeah. So this is the same as the identity, I guess. That should be correct. Submit. No. What is finite? Usually is finite not supported by the input types, and the input could not be safely. What is that? Is finite. Complex value matrix is unitary. Square complex value array. Is finite not supported for these type input types. Save. What? Convert the D type. Is I think what's happening here is the multiplication. I think this is what happens, right? I think I can just multiply it like this. Because if I don't do that, then it will tell me just that. Oh no, that's also a problem. Transpose conjugate operator. Transpose. That's weird. This is just me lacking knowledge of Python, I guess. I'll have to figure out. Okay, give me a second. Anyway, baby's up. So, I guess that's just a Python. I have to figure it out. Okay, but I'm looking forward to see. Oh, that gets a bit mathy. Kind of hate it but love it at the same time. We'll see. Sure that one follows from the condition. Blah blah blah. Some more mathy things. Cool, but it's good. So we talk about unitaries, and I think it's nice because so describe how unitaries arise from preservation of marginal probabilities. I guess it's gonna show us why the unitaries are, important for the evolution because they preserve. And I mean, the answer is because these are the matrices, they preserve the sum of probabilities as you keep operating them. So I think that's the reason. But they're gonna see probably mathematically how that gets derived, and then, yeah, bye bye.